Okay, so today we're going to discuss a very important topic, the application of the statistical mechanics to learning theory, seeing how we can use the tools that prove to work extremely well in statistical mechanics and in physics, may also be useful to study machine learning systems and maybe more general systems, not more general, but the other learning system that we encounter in nature, such as biological systems. So before we get into that, let me just emphasize on the two ways how we usually think about constructing theories. And in physics, it is known very well. In other branches, sometimes this strategy is a bit overlooked, so I'd like to emphasize it first. Now, if I'm starting saying something which makes no sense, it's because of the drugs that I took. As you all know, I'm sick. And so that's my excuse for today. I may not use the same excuse some other time. Okay, so what are the two approaches? Top down and bottom up. So the top down is you start from a theory, you develop your model, you do calculations, and then you extract from that experimental predictions. The bottom up, you do the opposite. You actually play with experiments first, you see some patterns, and then you propose a theory. What is often overlooked is that there is actually a very important layer in between theory and experiment. And in physics, we call it a phenomenology. Now, the idea that phenomenology, for example, the examples of a theory would be statistical mechanics. We're going to discuss this today, multi-level learning, something that we describe in context of biological systems, statistical mechanics of learning, which is actually the main topic of today's lecture. Now, phenomenology is something else, and it is examples of that would be thermodynamics of evolution, thermodynamics of learning, something that we will talk about next time. And experiments can be anything. It can be condensed matter experiments, and can be molecular biology experiments, or can be numerical experiments that you may do with machine learning systems. So the usual approach in machine learning that is mostly used is you start with a given task, and then a machine learning task, and then you propose an architecture based on your intuition, experience of what you've had before. So we're not going to take that approach. Instead, we're going to do something that is top-down. And the idea that we'll start with the theory of machine learning, which is what we described in the first two lectures. And then we'll try to extract predictions from those models that we described before for some simple models. And very often we'll be making assumptions and doing oversimplifications that may seem excessive. Nevertheless, there is a point for that. Once we derive those predictions, we say, okay, so we understand how the general principle works. Now let's generalize it. And this generalization is a key step. It's a key phenomenological step that we are making that will allow us to study systems that may not be able to calculate exactly mathematically, yet systems that we can use to model the experiments, either numerical experiments or as I already said, biological experiments. And once we have that generalization, and once we have this generalized description of system, or you may say phenomenological description, we'll be able to propose architectures of a given machine learning task. So that will be the strategy. So start with a theory, understand how the theory works in the statistical level, then generalize it, and then use those generalizations to develop neural architectures. Okay, so now let's dig a little bit deeper into what do we call about statistical mechanics. It's all about probabilities. It's really should be called a probability theory, but applied probability theory. A probability theory which can be used for modeling, let's say, physical systems. That would be statistical mechanics, the usual statistical mechanics, or biological system. That would be statistical mechanics of biological systems. In our case, our system is a machine learning system, so we want to understand probability distributions that involve the parameters of our system. Now, there are two types of parameters that we already discussed before. There are trainable and non-trainable parameters. For the starters, we only concentrate on distribution of non-trainable parameters, states of neurons. And we make an assumption that the trainable parameters are fixed. So they're fixed, and there are still some distributions of non-trainable parameters. Later on, we'll be studying evolution of those non-trainable parameters, and that description will follow in the 2 or 3 lectures from now. Okay, so what is the simplest distribution we can write down? Well, first of all, as we already discussed, any training data set is a probability distribution. It can be a probability distribution on the trajectories, and then it's more complicated, or just a probability distribution over states, like images or handwritten images of digits, right? And so we denote it for now, for simplicity, we assume that this is just a probability distribution with no ordering in this data. Okay, now, but that is only for the boundary neurons, for the input and output neurons. What we want to do, we want to write a distribution for all neurons, even the ones that are in the bulk. So imagine that you run your numerical simulation, you keep changing your boundary data, and then apply activation dynamics, and then the states of neurons in the bulk, in the hidden neurons, keep changing. So there is some distributions to that. In the coarse-grained sense, you want to be able to describe the distribution some way. And so one idea is to describe it this way, and that's called the microcanonical ensemble. It turns out that this ensemble is hard to handle because of the delta functions and hard to integrate. And the reason I call it microcanonical ensemble, it is equivalent to the microcanonical ensemble in physics, where the parameter that you fix is energy. You say, well, let's consider all states of the system with a fixed energy. You do not allow this energy even to change a little bit. Now, this is not very realistic. Usually, the system is in contact with the environment, and so there is energy exchange. And so instead of having a fixed energy, what you have average energy. And that's why this assumption of microcanonical ensemble often should be changed to another ensemble that we'll discuss on the next transparency, which turn out to be easier to tackle, to analyze. Okay, so then this is the distribution. So we have basically attached a delta function to the boundary distribution. And now we have a distribution of all neurons, or the neurons that are in the bulk and in the boundary. And given any distribution, you can calculate a quantity such as average loss. You can just integrate it, weight it by this probability distribution, and obtain your result. This is what is done here. Okay, now what about actually doing this in principle? You can do it computationally. You can do it on the computer. That involves calculating this of fixed point equation, the solution of the fixed point equation. And we actually do that when we run the simulation, right? You start with some input data, then you calculate the expectation, then you activate your dynamics. You have the signal to propagate through the entire network. You calculate X, then you can plug it into your loss function, and you can calculate the average loss. And you can keep doing it many iterations. You can do it over many epochs. And so this is something that you can obtain by brute force, right? Now, it would be nice if you could estimate this ahead of time. So without actually trying some B and omega and W, you would just actually calculate it ahead of time. And then you would know whether certain values of the bias or weights would lead to a good loss function or not. If you would know that, then you wouldn't have to do the brute force. You would ahead of time propose an architecture for which this loss function is small. But that involves this integral, right? And as I said, this integral is hard to do. There is no analytical expression that will enable to do that. There is a complicated function that appears inside. Okay, but the key idea is that it actually comes from the physics, is that to replace this difficult integration, which has a delta function, with a simpler integration. And the usual integration that we know how to do in physics is Gaussian integration. So replace the delta function with a Gaussian. And if you can do that, then you can easily calculate it, the Gaussian, and then obtain the results for what the loss function would have been without actually running the numerical simulations ahead of time. Now, this seems like cheating because you replace one distribution with another, and it is. However, in the limit when the number of neurons, or in physics particles, is very, very large, one can show that the two ensembles give you indistinguishable results. And so that's the idea, right? We have a difficult probability distribution. It's hard to do analytic calculations. We replace it with a simpler one, with a Gaussian. And then once we do that, all of a sudden we can do all the things analytically in certain limits and make predictions. Okay, that's one justification of using this other ensemble that I didn't even show you yet. Here's another one. It comes from James. He proposed the following. He said, I don't care what your system is. All I care is that there are some variables that you don't know about. And then that means that there is a probability distribution for those variables. And once you have that, tell me the only thing that you do know about the system. And given that information that you provided, I will be able to draw a probability distribution, which is the best one to describe your system. So once again, there are some parameters that you don't know. You think that there is a probability distribution for them. There is something, however, that you do know, and then use only that information to derive a probability distribution. Of course, there are many probability distributions that would satisfy this equation. And this equation tells you, well, the only thing I know about my system is its average loss equals to something. What James suggested is that among all of the probability distribution, choose the one that has the maximum entropy. And that it kind of agrees with the intuitive picture. If you, for example, know nothing about the system, not even this equation star, then most reasonable to say, well, all values of x are equally probable, so there should be a flat distribution. But if you do know something, that gives you additional information, and that you just use that additional information to derive a probability distribution. So this is a second take. If the first one you can think like physics motivated one, this one is information theory motivated approach. Why that probability distribution that I will be constructing, which is called canonical probability distribution, is the right one to use. But let's follow those steps carefully so that we know that we are not cheating anywhere. And the first thing by doing that, we'll derive the canonical probability distribution. And the second thing, we'll learn how to solve variational problems where you are trying to find a function which satisfies some condition. Usually when you minimize or maximize, right, you just have one variable that you like take left and right, you differentiate with respect to it and see when the value of the derivative equals to 0 and say, well, it has to be then a maximum or minimum distribution. Here, instead of the variable, we actually have p of x. We have the whole function that we can vary, we can change. And then we should just learn how to do that. And this is what I'll describe shortly. Okay, so but to summarize what I just said, this is the statement of the exact mathematical problem. We have this equation, which we'll call a constraint. It has to be satisfied to whatever p is. And we have this second equation that tells you what entropy is. And now we are trying to find the probability distribution which maximizes entropy, this S, subject to this constraint. That's all. Okay, to do that, one uses the Lagrange multiplier method. Basically, what you do, you construct this large function that has all ingredients in it. It has the entropy itself, S of P. It has this term, the second term, which is basically should be 0 if the condition star satisfied. And so by setting a variation with respect to beta to 0, will ensure that this condition is satisfied and u is equal to this integral. Okay, and the third term, well, we also need a third term because p is not just any function. It's a probability distribution that has to be normalized to 1. And so we want to impose the second constraint. So those two terms are called constraints, such that when we vary respect to nu, the integral of the function p of x actually equals to 1. Okay, so we have a function that we are trying to maximize. We have two constraints, and this coefficient beta and nu are called Lagrange multipliers. They multiply your constraint. Then what you have, this overall function depends on the three variables. Two just numbers, beta and nu, just multipliers. And p is actually a function, so it's a very different type of variable. Okay, so in mathematical terms, what we want now is we want to find a solution where this whole function is extremized. That would ensure at the same time that S is the maximum subject to those two constraints. And mathematically, we write those three equations. The second and third equations are very familiar. There's nothing just differentiation of a function with respect to the variable. It's a partial differential because function has many variables. But the first equation, it looks a little bit different. And so everybody who's in the physics department would know what it means, but in the computer science department, you would not necessarily have seen that. But it means it's called the variational derivative. Basically, you are varying this scalar quantity, this number, with respect to the whole function. So the px is actually a function. All right, so now let's see how that works and what kind of distribution we will attain. Because after those three equations are solved, what we want to have, we want a p of x equals to something, right? We want probability distribution to be given to us. What is the most reasonable distribution? What is the one that has maximum entropy subject to the constraint on the average loss and subject to a constraint that it is actually a probability distribution? As I already said, the first two are easy to do. So here I just copied this Lagrangian in the quotation marks because it's not the physics Lagrangian. And we just look at it and we differentiate with respect to beta. If you do that, of course, this first term doesn't depend on beta, so derivative will be 0. The third term also doesn't depend on beta. Only the first term depends, a second term depends, and it depends linearly. So once you differentiate with the beta, you end up with this. Now, here is a problem of a copy and paste. Basically, here was supposed to be a different equation that is not different now. And so let me maybe quickly change it. And as I do that, let me see if there are any questions that people might have. And I'll be more than happy to actually answer. Actually, maybe somebody can tell me, what do you think the second equation should have been? And that will probably be a good place to stop. Yeah, so what do you think?
This normalization constraint?
Yeah, so it should be nu, d nu, okay. And then what should be the result of the differentiation once you do that? So it should be
1 minus the integral d y cube.
Exactly. And we will put it right here. Let's see if I okay, so now if I stop sharing and then I start sharing again, and then I go to the respective place. Let's see if there, now we have a modified and improved. Yeah. Okay, so now this is what it should be, right? Okay, very well. Other questions since I'm now, yeah, if there are any other questions? Okay, so let's go. And so the third, of course, variation is the list known to physics. In fact, this one is easier than what we do have in physics. We always do this variation, and L is actually the real Lagrangian. And this function that we were with is the real field, as we call it. But in physics, it's a little bit different and a little bit more complicated. And the reason for that is because sometimes inside here, we have derivatives. And when you have derivatives, you have to carefully throw them around when you do this functional differentiation. Now, also note, I differentiated with p as a function of x. And here I assume that this one is a function of y. Now, this is to illustrate that this y is a dummy variable. Really, there is no y outside of this integral. And x is something that I take to be a variable from the outside. So it may also be convenient for you to think about this p instead of the integral, maybe a summation with some discrete values, right? And then you do just differentiate normally partially with respect to one of those variables. And that's kind of what is happening now. Really, the only difficulty would rise when you have derivative in here, which we will have in the future lectures, but not now. Okay, so now let's see how it works. Now I differentiate with respect to p. All three terms have p's in it, right? So the first term has p appearing in front of the logarithm and inside of the logarithm. So basically, when I differentiate with respect to this term, out of all integral, only the p which is at the point x would be non-zero, and at that point, log of p actually will be log of p of x, which is this term. Now but then of course p of x would also appears here, and when I differentiate log, I get 1 over p of x, which is cancelled with p of x, and you get 1. So that's how you get this minus log, and you get a 1. Now I differentiate this other term. U doesn't depend on p, but that thing does depend on p. And so by doing this differentiation, I just obtain h at the point x, b, w. And similarly here, multiplied by beta, because there is a beta and a minus sign. And the same here, when I differentiate it, basically px to px gives you 1, and there is a coefficient mu. So you get 1, 2, 3, all 4 terms that have to be set to 0. So note that out of those terms, really only one of them depends on p of x. That's great. That makes us allows us easily to solve this equation. Others don't depend on p of x, but they depend on x or either on the constants. So I can solve this equation and obtain my solution. P of x must be equal to the exponent to the minus beta h minus 1 minus nu. This is an exact solution. So if I know what nu is, this will actually be a legitimate probability distribution. Okay, now if I don't know what nu is, the very least I do know it has to be proportional to this exponent. And that is the exponent that you see everywhere in physics. This is sometimes called Boltzmann factor. This is something that you see in Maxwell-Boltzmann distribution, where here you have some velocity square appearing. You see it everywhere. This is of crucial importance. Now, also note that this p of x would appear inside of integrals. And so from the point of view of integration, it would be easier if this term is quadratic in x. If it isn't quadratic x, we actually don't know what to do. So basically, physics ran out of ideas. With the quadratic, we know how to calculate everything exactly. Once it has non-quadratic terms, that we didn't run out of ideas. The two types of ideas that we actually have to handle those problems is one is a perturbative analysis, and you might have heard about Feynman diagrams, etc. Those are ways of you to solve systems where this term is not just quadratic. There are also some duality ideas of how you can change the problem that is not very perturbative to a perturbative one. We're not going to discuss any of them now, although those other alternatives of how to actually solve system where h is not just quadratic are on the table, and they are important. And as I will argue, they are very important that you actually see those systems very fast in your learning system when you start learning. So quadratic is just a nice thing that you can do, but most of the real world things, of course, no one wouldn't have quadratic things here. Okay, so as I said, we're going to call this a canonical ensemble. It will simplify calculations, it is not exact. And so we always have to check whether our analytics agrees with the numerics. And if it doesn't, we should try to understand why. And very often it is because this h is not quadratic, and so our integral approximation wasn't correct. Okay, so what kind of integral approximations? It's described here. So just to summarize from whatever we discussed in the first half of the lecture, is that here is a proposal for a reasonable or maximum entropy probability distribution of only non-trainable variables, which, however, this whole distribution does depend on the extent of the trainable variables B and W's. But for the time being, they're frozen. The system, so you think about that, you stopped learning, and then you run through your epoch, and you are trying through the entire data set, and you're trying to construct the distribution of P of X. What is it? What kind of distribution it would be as a function of X? Okay, so now let's see. Now let's introduce the machinery of actually using this type of distribution to extract useful properties. The machinery is in mathematics known as a momentum generating function. In physics, it's known as a partition functions. They're very similar. And let's see how that works. So the idea behind momentum generating function is, instead of working with P of X, work with M of K, okay? So you perform this, it looks like a Fourier transform, but this one has here, it doesn't have a complex negative identity. It doesn't have I here. So it's a Laplace transform. But when you do that, what you get at the end, you get a function of K. And now, how is this function of K useful? Well, look at this. Let's say we do have M of K. Then if you plug K equals to 0, then what would be expectation value of 1, or it would be actually 1. It would just be a normalization. So we know what mu M of 0 should be. But the interesting one is when you take this function as a function of K and you differentiate it. Okay, so let's differentiate it. If you know this function, you can differentiate it. But when you do that, then this derivative, you can take inside, right? This P of X doesn't depend on K, and you differentiate the exponent with respect to K. So what happens, X jumps on front. Okay, then you have integral of dnx x px. You still have this exponent, but we again set K to 0, so this exponent goes away. And so by differentiating M with respect to K, first derivative, at 0, we can find expectation value of the variable X. When you do two differentiation, you will get the second derivative, and so forth, right? Because when you do the first derivative, one X jumps on front, and then you do the second derivative, another X jumps on front, then again you set your K to 0, so the exponent is gone, and you get expectation value. So that's interesting, right? So we've came up with a machinery. Think about this as a machinery of generating momenta, statistical momenta. And then you can forget about your P of X. This machinery, this M of K, encodes everything there is to know about probability distribution, at least when you can calculate it. Okay, so now let's think what we can do with the particular probability distribution. The idea would be the same, but now let's also take and now integrate our probability distribution that we already have. This is the distribution. It can also have other constraints. For now, I just wrote this constraints because this is what we derived by imposing only two constraints, but you can have more, of course. And so the form of this distribution can have other terms. For example, in the machine learning system, there is an additional constraint on X. For example, let's say you are using hyperbolic tangent as activation function, then the X cannot be larger than +1 and smaller than -1. So that is a constraint that you have to impose in the system. And then can be other constraints that just come from the training data set. All those constraints would have to be imposed if you want to approximate your probability distribution better and better. Okay, but the idea is that to do the same as you do here, put as many constraints as you want, and also sources. So this k of x in physics we call sources. So I can also put here k times x, and then put this large expression inside of the integral and then integrate it. Then x is gone, and then what we obtain, we just have obtained a function of the variables that are external to the system of axis of the neurons. And this function is a partition function. In physics, it's the single most important concept in statistical physics, because usually we may not even know what the fundamental theory is, and these things inside may be very complicated, and the integral may not be easy to calculate. Yet we can just model the partition function, and that would be enough. That would give us enough things to work with. And so the phenomenological approach would be, well, forget about this fundamental stuff, understand which things can be present, understand what are the general principle behind the partition function, and then try to generalize it. Okay, but before we go into the generalization, that will probably mostly be discussed next time when we discuss thermodynamics and phenomenological modeling. Let's have a simple example. Let's have a simple example when our probability distribution is given by this. Okay, so what is this? This first term looks new, but it isn't. This first term is actually comes from what we called bulk loss. So let me quickly go back. So this term has x, and there's some functional form of x, and then has again x, and then there's some function of x. F is our activation function, so it's nonlinear. And as I said, if this is nonlinear and this is nonlinear, this whole thing is not going to be quadratic. But maybe let's take a linear approximation of this function around mean value of the states of neurons. And if we do that, then this first term will be linear in x, this second term will be linear in x, and this whole thing will be quadratic in x. And if it is, we're in business. We can easily do the calculation. So if you do that, and I encourage you to do this, it's just a Taylor series expansion, then you will see that what you have, you have a quadratic form. You have a quadratic form in X with the matrix G that is obtained by doing the linear expansion of the bulk loss that I just showed you before. Okay, so then this really comes from our loss considerations. Now, the second term is motivated by the fact that the range of the states of neurons may be finite just to the way activation function is defined. So for example, for hyperbolic tangent, it would be between +1 and -1. Now, of course, this range has very sharp boundaries, and I'm just approximating the sharp boundaries with the quadratic form. Not exactly correct thing to do, but again, we're in business of first doing the quadratic approximation, which we can easily evaluate, and then studying perturbations away from it to see whether we can improve it further. Okay, so then this is from the first term is motivated by the loss function. The second term is motivated by the constraint imposed on the range of the activation function. The third term is can come either from, again, a loss function. We discussed it. You can have a binary classification task where the locally neurons would like to classify. Also, this may come from the actual data set. For example, you can have a data set which has two classes and it tries to classify, and if so, that would impose an additional constraint on this probability distribution coming from the data set itself. So if I would write in here some other non-quadratic terms, the calculations would be harder, and so I don't do it for now. I just give you 3 examples of where the quadratic terms would appear. But then if you have that, you can plug this probability distribution in here and then do this integral exactly. This integral is very easy to do. It's a Gaussian integral, and you obtain this result. And it has all the necessary ingredients here. It has this beta, that's a temperature, inverse temperature-like parameter. It has this G that represents the loss function, quadratic form of the loss function. It has this M, which may come from the boundary conditions. It has this 1 that comes from the fact that I'm assuming that it's a hyperbolic tangent. It has all of the ingredients. Now, what may happen is that when you do calculate it, you will end up that this determinant is negative. Now, if you do have that, then there is a problem. Now, when can this happen? Well, look at this G matrix. Think about going to the space, to the bases where G is diagonal, meaning that in the diagonals, you have all of its eigenvalues. Now, if there is a direction where the eigenvalues are negative, that means that in that direction, you have not negative x squared in that direction, you will have a positive x squared in that direction. And so you will have a probability distribution, which instead of being Gaussian, is something like e to the plus x squared. So it's not normalizable. And if it's not normalizable, then of course you cannot take this, you cannot do the integral. And so of course you'll get the wrong answer. However, if all of the directions, if this whole overall function matrix has all of its eigenvalues positive, then you're in business, and then there is no issue. Okay, so are there any questions? So let me just summarize what we did. All right, we started with the difficult probability distribution. We called it microcanonical. We said, all right, yes, we can calculate it exactly. We can calculate it in the computer, but it is hard to understand where things are coming from within that function, within that distribution. So let's, instead of working with the delta function, let's instead consider Gaussian distribution. We know from physics that in the limit of the large number of particles or neurons, the two are really indistinguishable. And then we motivated that canonical ensemble with the maximum entropy principle. We derived it. Good. So then we said we still need the machinery to work with, and we just starting to develop this machinery. And the machinery is machinery of the partition function. We say, all right, yes, it is true that we now have a canonical ensemble. It is true that now our distribution has to be something like exponent minus beta h, maybe some other terms. But we do know that h may be complicated, the other terms may be more complicated. And so maybe it will still be hard to do this integral. And we say, yes, this might be the case. Nevertheless, let's start doing things with when it is calculable, when you can do that. And then we'll see when our theory actually breaks down, where certain things starts falling apart. And for that, we said, okay, when we have that, let's introduce the separatus of the partition function. Now, we will be using heavily this partition function next time, but as a preview to that, I describe how the moment generating function works. Basically, if you have an integral like that and you know result of this integral, just by doing simple differentiations of this result, you'll learn a lot of things about the probability distribution. We'll be doing the same here. As a preview, just think about differentiating the z with respect to beta, right? If you do that, h jumps on front. And so what you have, you kind of get something like expectation of h. And that is u, this is average loss. So getting average loss from this z will be easy. And many other things, many other thermodynamic things that we'll discuss. But for now, we said, well, let's not worry about this general form. Let's concentrate on a particular form, on a form where the integral is easy to calculate. And that is actually a quadratic form in the exponent. And in this case, the integral is Gaussian. And then we derived that result that has all the pieces in it. All right, let me see if there are any questions before we go on. So let me now demonstrate to you what this G matrix is. It seems to be important here, and it seems to be a dynamical object when things evolve. Okay, Fikra, go ahead.
Can we do one example when, for example, beta is 0?
Sorry, I cannot hear you. Can you repeat it?
Oh, can you do an example when beta is 0, for example?
Yeah, so if beta is 0, then you don't have this term, right? Then you just have that. And so you have just this. And it's a trivial example, right? So you have a determinant of 1 minus m. It would be 1 minus m to the power of how many, so it will be like trivial example. The most interesting part about machine learning is actually hidden in this G. And this is exactly what I'm going to talk now. I'm just going to show what this G is. For people familiar with the graph theory, I will make one comment. And the comment is this: G is actually very, very closely related to Laplacian on a graph. Okay, how? Let me emphasize, well, first of all, it's a very important point because we know we have a machinery and we know how to, what Laplacians on the graphs are. That's the first point. The second point, it is also related to the usual Laplacians that we use in physics, where the Laplacian is just the diagonal matrix of second derivatives. Okay, now why is this like a Laplacian in the graph? Well, forget about this f prime for now and only think about W's. W's is like your adjacency matrix. Okay, and so basically your when you take this first term I minus W, this is like you're taking a derivative in the direction of where the edge is coming from. So you're trying to find the difference of the states of the neurons and the two neurons, right? And the two difference in their states in the two neurons that are connected by this weight matrix. And then here you square it. So this is intuitive way. So you should intuitively think about this first part as a first derivative. The second part is the second derivative. And so together it's a matrix of second derivatives. Okay, now this is one comment. So it connected to the Laplacian of the graph, and this W should be thought as the adjacency matrix. Now, the other point is that we do know a lot about Laplacians, and when we look at their spectrums, from the spectrum of the Laplacian, we may be able to infer what is actually the structure of the neural network. There is a famous mathematician paper called "Can You Hear the Shape of a Drum?" Right? From the spectrum of a certain operator on a certain manifold, can you know what is the manifold is? And usually you can. Of course, there are some counterexamples, but this is something that just to tell you, to emphasize the point that once you do know what G is and you do know what its spectrum, meaning all of the eigenvalues, you can infer about what is the structure of the neural network is, and how can I improve the learning, but by changing or change learning by changing this spectrum, by changing the neural network. So in what follows, I'll show you this matrix G for two types of networks. One is shallow, and the other one is deep. Both new networks were trained on the same data sets, NIST data set of handwritten images, and we'll see how both spectrums evolve. So we will see how what is G in the initial conditions and how it gradually changes. Now, G is a very large matrix, and so I cannot actually show you the matrix. What I'll be showing you, I'll be showing a distribution of its eigenvalues. Now, this is a symmetric matrix, so all of its eigenvalues will be real. However, there will be have a distribution of them. Now, also all of them have to be positive, or otherwise this would be divergent integral, right? So all of them will be positive. They will evolve somehow, And the one last thing, what I'll be plotting their distribution. Because there are many of them, I cannot just show you all of them. I'll be plotting their distribution, and not just distribution of the logs of those eigenvalues, because they're all positive. There is a reason for all of that. We may not have time to go over this today, but we will definitely describe it when we discuss efficiency of learning, when we discuss which kind of networks are preferred, which kind of spectrum of G are preferred for the neural network to learn. So this is the first example. We take that matrix G, or you may think log of that matrix G, or the log of its eigenvalues, and we plot a probability distribution of that. So this is the initial distribution. So we have some negative logs, meaning that the eigenvalues are very small, and then positive logs, meaning the eigenvalues are large. So we have some small, some large eigenvalues. This is how system evolves after 100 epochs of training. This is what happens after 1,000 epochs of training. This is what happens after 10,000 epochs of training. One thing you can note here is that the distribution is completely symmetric. It's not completely symmetric in the beginning, but then eventually it becomes more or less symmetric. For any eigenvalue on the left, there is eigenvalue on the right. Something that we do not know, do not impose on the system, but it is something that you will see as it evolves for the shallow neural network. There are derivations showing why this happened, and we'll discuss it later. But this is actually showing you that the eigenvalues are not unrelated. They're coupled, right? You have for every one on the left, you have the one on the right. And that reduces the effective dimensionality of the learning system. So it's no longer learns and allows its eigenvalues to be whatever it wants. It constrains itself. It reduces the dimensionality by a factor of 2. So effectively, you are in a smaller space when you use a shallow neural network. The space of possible G matrix. Remember, G matrix is the key to learning, right? You want to change this G matrix in the right way. Well, you want to change the weight matrix in the right way, but after that, you will produce the right G matrix. And so the shallow network, if you impose a constraint on your neural architecture, such that it is shallow, it has few layers, right? It's not unconstrained like we discussed in the previous time. It's very much constrained. Not only it's constrained to have very few layers, then you have this picture. I'll show you, unless there is a question about this, I will show you the other one and then I'll take questions. Okay, so the other one is a deep neural network. And it's completely different. Now the symmetry is broken. You do not have a symmetry between negative and positive logs of the eigenvalues. And moreover, you see there's tail developing. There is a runaway eigenvalues to the left. You see the sum of the eigenvalues become very, very small. Logs of the eigenvalues become very small. See, they become very, very small. It goes to -4. Okay. And if logs of the eigenvalues become very small, it means that lambdas are very small. Well, okay, well, let's go back to our distributions and think about what it means. So we have some directions where lambdas become very, very small. Well, this means that these directions are almost flat. So instead of having a good Gaussian, the Gaussian hill starts spreading out. Okay, and eventually what you can see from direct simulation, instead of having a hill, it starts to developing 2 peaks, and certain neurons start to classify left and right. And the indications for that is exactly this runaway eigenvalues. Of course, this is what both networks wants to do. However, the shallow networks cannot do that much because the small negative logs of eigenvalues are attached to the positive logs of eigenvalues. And here they're completely detached. And so they can freely move. All right, let's see if there are any questions. This is a kind of, this is our first result when we made a simple assumption, Gaussian assumption, We performed statistical analysis, we performed simple differentiations. We identified the important matrix, and we said, all right, let's study the spectrum of this matrix, and let's see how this spectrum affects the learning efficiency and how things work. And more detailed analysis of the matrix G and of the actually partition functions more generally. They're connected, right? Partition function is connected to G. More general of those analysis of those two things will follow, but this is like our first attempt to understand what they mean. Are there any questions?
Just out of curiosity, can you hear me okay?
In your simulations, all eigenvalues was positive?
Say it again?
In your simulations, all eigenvalues was positive?
So eigenvalues of this J matrix, they remain positive. Yes. Now, but this is very much constraints neural network.
Mm-hmm.
So it is nilpotent weight matrix. And so, and for that, it was a feed-forward neural network. And so all of them remain positive. Yes.
And then I had a question. So just out of curiosity, just going over the shallow and deep results, did you do intermediate results between the shallow and deep networks to see when the regime was crossed?
Say again. What?
Sorry. We can obviously see the difference in the distribution between the shallow and deep networks. Did you do any numeric experiments to show the crossover between the behavior of G in those experiments as well? Just out of curiosity.
Well, the only that's the only simulations that I've done, nothing else, right? Okay. So I haven't studied it. The one that I looked at and was interesting for me is that this looked very symmetric, and then I was all able to prove it analytically why it is symmetric, and it's a feature of the small number of layers. With a large, there is no such constraint, and this is a skewness of the distribution, and so. Now, how do they interpolate between one and another? There would have to be more analysis of. Yeah, it is a lot more to be done. This is just, I guess this is an illustration of why the G matrix is important, and also what it tells us for the statistical properties like partition function that will be analyzed.
Okay, thank you.
Sure. Other questions?
Was this supervised or unsupervised learning?
Oh, this was a classification of handwritten images, so completely supervised. The simplest thing you can do, again, first attempt to see. There's a combination of two things, right? So there are statistical parameters that are in Z. As we will see, Z is related to the free energy, and we'll discuss it next time. And the second is spectral properties of G, so how they kind of interplay. There are two types of analysis that you can do. Now, of course, ideally what you want to do, you want to perform this analysis, say, okay, well, your network is a poor learner because when I calculate the, its spectrum, it is symmetric or it's constrained, or, there's some problem with the G, with the spectrum of the G. You identify it and they say, well, that's your problem. Now, of course, G is a spectrum. It's a fine grade analysis. Now, coarse grained analysis is the Z, like when you clump together all of the eigenvalues. And then you can say, all right, so now instead of me telling you which eigenvalue is bad in your neural network, I just calculate Z and say how to improve the further. So the idea is to do these calculations ahead of time, right? So then correlate, say what kind of spectral properties are important for learning, and what kind of statistical properties are important for learning. Okay, other questions?
Instead of maximizing the Shannon entropy, can you minimize something else? Is there something dual?
Okay, so that goes back to this question, right? So why would you want to maximize the Shannon entropy? I think there's like there's no reason to not do that. Basically, I think this is more or less trivial and also brilliant idea of Jane's, that basically, if you don't know something about the system, just don't make any assumptions. Okay. Now, if you do know something about the system, put it as a constraint. That's it. That's like, you know, 2 sentences summary of the result. Now, sometimes people say, well, maybe for some problems I should not be using the maximum entropy principle, I should be using something else. Then I think you are just not specifying what is it that you do know about the system. And if you are explicit about what you do know, and you put it in a constraint, I think this usually works. Of course, you know, there are examples. Now, and I'll make one more comment. This is so far only applies to the systems that reach some kind of equilibrium, right? When things stop changing fast. We will discuss a situation where things do change. And so basically you can apply your maximum entropy principle for at each moment of time, but the distribution is evolving. So this is a non-equilibrium thermodynamics. And then the claim will be that there is a generalization to the maximum entropy principle, which is only talking about states, generalization to trajectories. Remember last time we talked about how the probability distribution can be defined on states, or it can be defined on trajectories. So this is for now, we're just defining not on trajectories, but on states. And so the maximum entropy principle is correct. However, when you do go and you're trying to define some principle for trajectories, well, the claim will be that you have to switch from the maximum entropy principle to the maximum entropy production or minimal entropy production, stationary entropy production principle. So instead of looking at the entropy, you have to look at how the entropy changes, but we're not there yet. Okay. So again, to summarize, we described the 2 types of probability distributions. We discussed 2 types of probability distributions. We argued there will be a 3rd type of probability distribution, which will be very important. So microcanonical is hard to integrate. Canonical is easier to handle analytically. There will be a grand canonical. It will be more important in the future lectures. And that is when the number of particle changes, or in our case, number of neurons changes. What do you do then, right? Then how do you go about analyzing such systems? So we'll leave it until later. For now, we just described 2. We decided to work with canonical because it's easier. We do not expect it to be different when the number of neurons is large. The second idea was that when you have that, and when you have all the constraints and you already have your distributions, the good analytical expression to analyze is the partition function to calculate. Now, yes, calculating partition function may be a challenge, but let's not give up quickly. Let's first do it for quadratic functions where we know how to do things, and then see when this Gaussian integral is violated. When you have some kind of phase transitions, it will be violated when your single peak becomes 2 peaks. All right. So, and that is actually what I wanted to now talk about for the next few minutes. Is this the phase transition? So now phase transitions are extremely important in physics. It's suggested that those phase transition happens also in machine learning systems when the system may be in one equilibrium state and then it learns, and then all of a sudden it goes into the other equilibrium stage suddenly. So here's an example what I think was a phase transition in this machine learning system, although I think in a machine learning system, the phase transition happen all the time. Now, why do I say that they happen all the time? Well, you can numerically observe that you look at the single neuron, you see how the distribution of its state changes. First, there is a single peak, and then it splits into 2. That's a phase transition. You have first, it was favoring to be. This is the same what we discussed for the matrix G. When the matrix G all of a sudden starts angular values of matrix G all of a sudden it becomes small. So this is when one of the eigenvectors of this matrix become negative. And that is when the eigenvectors of the matrix G become smaller than this factor. Okay, then the phase transitions takes place. And that will keep happening with the different eigenvalues one after another. And as I said, the Gaussian peak will be splitting in the 2 and 4 and so forth. But you can probably also observe it in the behavior of the loss function. So here I'm plotting two things. I'm plotting the loss functions, which I call the bulk loss, and the other one, which I call the boundary loss. This is just one of the tests that you can do to see this phase transition. The other test would be actually to study the distribution of the states of the neurons that develops those peaks, or in the distribution of the matrix G. But here it's interesting. The reason I plot it is because it's interesting and also intuitively easy to understand result. So now vertically is the bulk loss function, which kind of, instead of if you recall, there was a loss function where instead we fix the boundary and we allow trajectories in the bulk to have uncertainties. The fixed point equation was not solved exactly, but the boundary conditions were solved, satisfied exactly. As opposed for the boundary loss, when the fixed point equation is solved exactly, but there can be mismatched in the boundary conditions. And you can think about this as one tells you from the point of view, the interior of the network, how well it performs. And the other one is from the exterior of that network, how well it performs. We usually just pay attention to this. If it gives the right answer, we're happy, but we are not worried about how far away your fixed point equations are from the minima. But what happens is interesting behavior. They both decrease, but then there are sudden jumps, 1, 2, 3. And those jumps represent kind of a phase transition where nothing much changes in the boundary. It's gradually learns, but the bulk states all of a sudden switch their meaning. Like, there's some bulk neuron that all of a sudden starts to classify and then reduces its error. This is just an interesting graph to motivate it. This type of discussion. It's also interesting in the context of the students learning, right? This horizontal line may represent your grade, and it may be like slowly changing, but then this one represents your actual knowledge, which all of a sudden there is kind of aha moment. You understood something, and there are certain neurons rewired itself in the right way, and there's some bunch of discontinuous jumps actually happen that may not be possible to evaluate objectively from the outside, but is actually happening inside. Okay, now this is more of a motivational slide. Now, more precisely, this type of phase transition were studied in the paper which called Emergent Scale Invariance in Neural Networks. We will discuss this paper further. And the reason why we think that what we are observing is a cascade of phase transitions, because you only see power law-like behaviors in critical systems that are very close to the phase transitions. If they are not critical, if they are far away from the phase transitions, then you usually sit in one minima and no power law correlators appearing, and there is no scale invariance. Again, this is more of advertisement of what we're going to study in one of the few lectures. But the point is that when this happens, when the eigenvalues become too small, this Gaussian distribution analysis is no longer correct. In fact, your G matrix may not even tell you what the right distribution should be. But there is a correct analysis in which by just doing the brute force numerical simulations. And in this analysis, you can see this cascade on the phase transitions. Now, there are two reasons why the phase transitions can take place. And that can be due to the dynamics of the non-trainable variables. And that would be the dynamics of the actual variables we are discussing statistically in this lecture, right? So now boundary changes, or activation dynamics changes. Something happens with the non-trainable variables. There can also be phase transitions due to the trainable dynamics. The system learns, and then all of a sudden it finds a new minimum. So it goes there, phase transitions. So both type of phase transitions would be important, interesting advice. You can also think about how can you enforce the phase transition to take place by changing the boundaries. What can you do with the boundaries so that you encourage the system to undergo phase transition? Or other way around, if you don't want it to undergo phase transition, what do you do? How do you handle that? So all this will, again, there are not many studies of the phase transition in machine learning, and this is a very interesting, important directions to proceed, either again numerically or analytically. Okay, are there any other questions? So let me I'll take questions, but this will be the strategy. So the next time, what we'll take this partition functions and say, yes, we were able to calculate it for the Gaussian ensemble, and that was relatively easy and struck information, but what we can do beyond that? We may not know how to do the integral, but can we still measure things numerically, and can we model the partition function itself, or as we will see, free energy or other things that are related to that? And that is the phenomenological layer that I described in the very first slide. You do calculations for models that you can, and then you generalize it, at that level of the partition functions of the free energies, things that we actually call thermodynamics. I think that is it. Any other questions? All right, so let me now stop share and stop recording.